Assalamu alaikum students. In this lecture, we will have a look at the equivalent circuit of a transformer. An equivalent circuit is basically a circuit representation of the equations that describe the behavior of the device. So first of all, we will discuss the different parameters of an equivalent circuit. After this, we will draw the equivalent circuit of the transformer. As we know, an ideal transformer is a lossless device. But in real transformer, there are different types of losses occurs. The diagram of real transformer is shown here. As you can see in this diagram, there are two main windings. The first one is the primary winding and the second one is the secondary winding. As we have already discussed, the winding which is connected to the power source is called the primary winding, and the winding which is connected to the load is called the secondary winding. This is the primary leakage flux and this is the secondary leakage flux. As we have already discussed, leakage flux is the flux which breaks out of the core and passing through the surrounding air. And this is the mutual flux. Mutual flux is the flux which remains in the core. The flux which remains in the core is called the mutual flux. So there are different types of losses occurs in real transformer. The first one is the copper or I2R losses. The second type of the losses is core or iron losses. The third type is leakage flux, and the fourth parameter is core excitation effect. So these are the different types of losses which occurs in the transformer, in the real transformer. So first of all, we will discuss the different types of losses step by step. And also we will discuss the equivalent circuit parameters for different types of losses. So the first type of the losses is called copper or I2R losses. Copper losses is basically due to winding resistance of the transformer. As you can see in this figure, there are two main windings. The first one is the primary winding and the second one is the secondary winding. Copper losses is basically occurs due to winding resistance, that is due to winding resistance of the primary winding and due to the resistance of the secondary winding. So copper losses is basically occurs due to these two windings. The first one is the primary winding and the second one is the secondary winding. We can calculate the copper losses by using this formula. Copper losses is equal to I2R. As you can see in this formula, the relationship between copper losses and the square of the current is directly proportional. It means when the current will increase, then the copper losses will increase as well, because the relationship between the copper losses and the square of the current is directly proportional. So copper losses is basically depend on the current. That's why copper losses called load dependent losses. It means when we will change the load, then the value of the current will change. When the value of the current will change, then the value of the copper losses will change as well. That is, when the load will increase, then the current will increase. When the current will increase, then the copper losses will increase as well. So that's why these losses are varied with load. It means copper losses are not constant in any transformer. Copper losses are varied with respect to load. When the load will change, then the copper losses will change as well. In an equivalent circuit, copper losses are modeled by placing a resistor in the primary circuit, that is Rp in the primary circuit and Rs in the secondary circuit. When we will draw the equivalent circuit, in the equivalent circuit we will show the copper losses, that is our resistors Rp in the primary circuit and the resistors Rs in the secondary circuit. When the value of the resistance will be minimum, then the copper losses will be minimum as well, because the relationship between the winding resistance, this is the winding resistance, that is the primary winding resistance and the secondary winding resistance. When the value of the resistance will increase, when the internal resistance of the winding will increase, then the copper losses will increase as well. So that's why when the value of the resistance will be minimum, then the copper losses will be minimum as well, because the relationship between the internal resistance of the winding and the copper losses is directly proportional. So in an equivalent circuit, we will show the copper losses with Rp in the primary circuit and Rs in the secondary circuit, because there are two types of windings in the transformer. So the second type of the losses is called core or iron losses. As we know, core or iron losses is the combination of eddy current and hysteresis losses. That is, the combination of eddy current and hysteresis losses is called the core or iron losses. This is the core of the transformer. These losses, that is core losses or eddy current and hysteresis losses, is basically occurs in the core. These losses, core losses, is basically occurs in the core of the transformer. It is the function of the voltage. Core losses is basically the function of voltage, not the function of the current. When the voltage will change, then the core losses will change as well, as we have already done in the lab. When we will find the core losses of the transformer, that is, when the value of the voltage will vary, then the core losses will vary as well. And in case of transformer, voltage of the transformer remains constant. Due to this, core losses of the transformer remains constant, because the voltage of the transformer remains constant. Core losses is not depending on the current. Core losses is basically depending on the voltage, and the voltage of the transformer is basically constant. Due to this, core losses remains constant in the transformer. Eddy current losses are resistive heating losses in the core of the transformer, and hysteresis losses are associated with the rearrangement of the magnetic domains in the core during each half cycle. As we have already discussed in detail in the start of the in the third lecture of this subject. These two losses we have discussed in detail. So this is the core or iron losses. Now, the third type of the losses is called the leakage flux. As we have already discussed, the leakage flux is the flux lines which break out of the core. As you can see in this figure, this is the leakage flux. It is the flux lines which break out of the core and pass through the surrounding air back to the other end of the winding. So this is called the leakage flux of the primary winding, and this is the leakage flux of the secondary winding. The leakage flux occurs both in primary and secondary circuit. We represent the leakage flux with flux LP in the primary winding and flux LS in the secondary winding. For primary circuit, the leakage flux is basically flux LP. L means leakage and P means primary. Now the important question is, how will the leakage flux represent in an equivalent circuit? So this is the very important question. How will the leakage flux represent in an equivalent circuit? It means, is the leakage flux in the form of resistance or in the form of inductance? So this is the important question. That is, how will the leakage flux represent in an equivalent circuit? As we have already discussed, the leakage flux in the primary winding is flux LP. The induced voltage due to this leakage flux is E is equal to NP d phi over dt. When the leakage flux will be more, then the induced voltage will be more. When the leakage flux will be less, then the induced voltage due to leakage flux will be less as well. Similarly, the leakage flux in the secondary winding is flux LS. L means leakage and S means secondary. The induced voltage due to secondary leakage flux is E is equal to NS into d phi over dt. It means the relationship between the induced voltage and the leakage flux, the change in leakage flux is directly proportional. When the leakage flux will change more, then the induced voltage will be more. So this is the equation of leakage flux in the primary winding, and this is the equation of leakage flux in the secondary winding. Now we will find the value of the leakage flux, because our main objective is how will the leakage flux represent in an equivalent circuit. Because in an equivalent circuit, we normally use the parameter in the form of resistance or in the form of inductance or capacitance. So this is the equation of leakage flux in the primary winding, and this is the equation of leakage flux in the secondary winding. According to Ampere law, the relationship between flux and current is directly proportional. When the value of the current will be more, then the value of the leakage flux will be more, because according to Ampere law, the relationship between flux and current is directly proportional. That is, I directly proportional to flux. When the value of the current will be more, then the value of the flux will be more. And we have also discussed the relationship between flux and reluctance is inversely proportional. Reluctance is basically the opposition of flux is called the reluctance. When the reluctance will be more, then the value of the flux will be less. It means flux is basically directly proportional to current and inversely proportional to reluctance. Therefore, flux will be equal to reluctance. Therefore, flux will be equal to NPIP over, in case of primary winding, leakage flux of the primary winding will be equal to NP. N means the total number of turns, I means current per turn, NPIP over R. R means the reluctance, because the relationship between flux and reluctance is inversely proportional. As we know, the reciprocal of the reluctance is called the permeance. permeance is basically the reciprocal of the reluctance. So that's why here we write the permeance P instead of 1 over R. We can write here NPIP over R, or 1 over R is basically equal to P. P means the permeance is basically the reciprocal of the reluctance. So therefore the formula of the leakage flux is permeance into NP into IP. I means primary current and P means primary number of turns. When the value of the current will increase, then the leakage flux will increase. When the value of the reluctance will increase, then the flux will decrease. So similarly, in case of secondary winding, the formula of the leakage flux is equal to permeance into NS into IS. NS means secondary number of turns, IS means the current per turn. And as we have already discussed, permeance is basically the reciprocal of the reluctance, that is P is equal to 1 over R. That's why here we write down the permeance. We can write here the reluctance. If we write this equation in the form of reluctance, then the flux will be equal to NPIP over R. If we write the equation in the form of permeance, then this equation will be equal to PNP into IP. Now we will put the value of leakage flux in the primary winding and leakage flux in the secondary winding in these two equations. The leakage flux of the primary winding, we put the value of leakage flux in the primary winding in this equation, and the leakage flux of the secondary winding in this equation. So we will get, so putting the value of leakage flux in the primary winding in this equation, we get E is equal to NP into dP NPIP over dt. Just putting the value of leakage flux in the primary winding is equal to PNP into IP in this equation, we get, after multiplication, N is basically the constant. Total number of turns in any transformer is constant. That's why we will take NP and permeance outside from this derivative. The final equation will become E is equal to NP into NP is basically NP square into PP means permeance into DIP over DT. So this is the equation of the induced voltage due to leakage flux in the primary winding. Similarly, in the secondary winding, we will put the value of leakage flux in the secondary winding is equal to PNS into IS. In this equation, we get E is equal to NS into dPNS IS over dt. Similarly, NS into NS after multiplication, NS square P into DIS over dt. So this is the induced voltage due to leakage flux in the secondary winding. Now, as you can see in these two equations, this is the constant factor. In the primary equation, NP square into P is the constant factor, and in the secondary leakage flux induced voltage, NS square into P is the constant. This constant is basically called the linkage reactance. The linkage reactance, that is L is equal to N square into P. N square into P is called the linkage reactance. P means the permeance, N means the total number of turns. The combination of these two is called the linkage reactance. So this is the important factor. This is the important equation. So that's why the leakage flux will be modeled by the primary and secondary inductor, or by primary and secondary reactance, because the leakage reactance is basically equal to N square into P. Is basically N square into P is basically equal to the linkage reactance. So that's why the leakage flux will be modeled by primary and secondary inductor, or by primary and secondary reactance of the inductor. So when we will present the leakage flux in an equivalent circuit, we will present it with the inductor or the reactance of the inductor in the primary and in the secondary circuit. So this is the equivalent circuit parameter of the leakage flux of the transformer. Now we will discuss the last parameter, that is how can the core excitation effects be modeled. As we know, in core excitation, that is in case of core excitation, excitation current is basically equal to I excitation is equal to magnetization current plus core loss current. As we have already discussed, excitation current is basically is equal to magnetization current plus core loss current. The magnetization current is basically lags the applied voltage by 90 degree. That's why it can be modeled by XM reactance in the form of reactance. The reason is that, as we have already discussed in detail, the magnetization current is basically lags the applied voltage by 90 degree. As we know, in case of inductor, current is basically lags the voltage. So that's why we will present this in an equivalent circuit by reactance XM. And the other parameter is core loss current. The core loss current is basically in phase with the applied voltage. It is also, we have already discussed in detail, the core loss current is in phase with the applied voltage. As we know, in case of resistance, voltage and current are in phase. So that's why it can be modeled by RC. It means core resistance. We will present the excitation effect with XM and RC. These are the core elements or core parameters. So these two are the core parameters, and this is the leakage flux parameters. And we will present the copper losses with resistance RP in the primary circuit and RS in the secondary circuit. We will present the leakage flux in an equivalent circuit with inductor, that is in the primary reactance and in the secondary reactance with inductor. And we will present the core excitation effect with XM and RC in the core. So these are the parameters which we will use to draw the equivalent circuit of the transformer. So the equivalent circuit based on these parameters, that is copper losses, leakage flux, core excitation effect, is shown here. As you can see in this diagram, there are two main parts. The first one is the primary circuit and the second one is the secondary circuit. As we have already discussed, copper losses is basically, we will represent the copper losses with RP and RS. RP is basically primary winding resistance and RS is basically secondary winding resistance. So that's why copper losses is basically shown here in the form of RP and RS. This is the RP and this is the RS. These two is basically show the copper losses equivalent parameters. And we have already discussed the leakage flux we will present in the equivalent circuit in the form of reactance, that is in the primary reactance XP and in the secondary reactance XS. So this is the primary reactance and this is the secondary reactance. This reactance is basically due to leakage flux of the primary winding, and this reactance is basically due to leakage flux in the secondary winding. So the third parameter is core excitation. As we have already discussed, core excitation, there are two parameters, that is RC and XM. XM means magnetization reactance, RC means core resistance. So these are the core parameters. So we will show the core parameters in the primary side, because in the core the flux is basically produced due to primary winding. So these are the core parameters we will show in an equivalent circuit in the primary side. So this is the RC and this is the magnetization reactance. These two are the core parameters, and these are the parallel with the primary copper losses and the leakage flux reactance. So this is the equivalent circuit of the transformer. In this circuit, RP and RS is basically show the copper losses. When the value of RS and RP will be more, then the copper losses will be more. When the value of RS and RP will be less, then the copper losses will be less. This reactance, that is XP and XX, is basically due to leakage flux. When the leakage flux will be minimum, then the value of the reactance XP and XX will be minimum. So these are the parameters due to excitation branch, that is due to the core loss current and magnetization current. So this is the primary number of turns and this is the secondary number of turns. So this is the exact equivalent circuit of the real transformer. Now, to analyze this circuit is very difficult because of the transformer in between. To solve this circuit is very difficult because there is a transformer in between, that is in between primary and secondary. So we need to remove the transformer if we want to solve this circuit. So first of all, we need to remove this transformer. Also, it is not simply remove this transformer because primary and secondary circuit is working at two different potentials. If the transformer is step up, then the primary and secondary will be in different potentials. The solution of this problem is we need to convert this equivalent circuit either its primary side or to its secondary side. It means the solution of this problem is, that is, we want to remove the transformer in this circuit. If we want to remove the transformer in this circuit, after this we can solve this circuit. If we want to remove the transformer in this circuit, so we need to convert the secondary side into primary circuit or primary circuit into secondary circuit to remove the transformer. So this is the solution of the problem. Otherwise, it is very difficult to solve the circuit with transformer. So our first objective will be to remove the transformer and convert the circuit from secondary to primary or primary circuit to secondary circuit. Therefore, we can convert the primary side into secondary side and secondary side into primary side by impedance transformation method. As we have already discussed in the last week lecture, we can convert primary side into secondary side and secondary side into primary side by impedance transformation method. So we have already discussed the impedance transformation method in the last week lecture in detail. So by using this method, we can convert primary side to secondary side and secondary side to primary side. So by using these formulas, we can convert primary side into secondary side or secondary side into primary side. The first one is the voltage source. As we know, Vp over Vs is equal to A. A means the turn ratio, that is Np over Ns. If we want to find the value of primary voltage, then the value of the primary voltage Vp will be equal to A into Vs. A means turn ratio, A is equal to Np over Ns. It means we can convert secondary voltage into primary voltage if we multiplied the secondary voltage with the turn ratio. If we multiply the turn ratio with secondary voltage, then the secondary voltage we can convert into the primary voltage. So by using this formula, we can convert the secondary side voltage source into primary voltage source. And if we want to convert the primary voltage source into secondary voltage source, then the value of Vs will be equal to Vp over A. If we divide the turn ratio into the primary voltage, if we divide the turn ratio with primary voltage, then the voltage will be equal to the secondary voltage. By using this equation, we can convert the primary voltage source into secondary voltage source. Similarly, as we know, Ip over Is is equal to 1 over A. We can convert the secondary current into primary current after that dividing by the turn ratio, that is Ip is equal to Is over A. If we divide the secondary current with turn ratio, then we can convert the secondary current into primary current. Similarly, we can convert primary current into secondary current after the multiplication with turn ratio with the primary current. If we multiply the turn ratio with primary current, then we can convert the primary current into secondary current. Similarly, we can transform the impedance from one side to the other side. If we want to convert the secondary impedance into primary impedance or secondary resistance into primary resistance, then just multiply the A square into secondary resistance. If we multiply the A turn ratio square into secondary resistance, then we can convert this secondary resistance into primary resistance. Similarly, we can convert the secondary impedance into primary impedance after the multiplication of A square. If we want to convert the primary impedance into secondary impedance, then we will divide the turn ratio square, that is A square. So by using these formulas, we can convert the transformer equivalent circuit from primary side to secondary side or from secondary side to primary side. So these are the very important equations. So now, first of all, we convert the secondary side into primary side. It's called the equivalent circuit referred to its primary side. It means in this case we convert the secondary side into primary side. It means the primary parameter will remain same. So our main objective is to convert the secondary side parameter into primary side. If we convert the secondary voltage source into primary voltage source, as we have already discussed, we just multiplied with turn ratio. And if we want to convert the secondary current into primary side, then we will divide the turn ratio A. So if we want to convert the impedance, the resistance or reactance from secondary side into primary side, then we will just multiply it with turn ratio square, that is A square. So this is the equivalent circuit. In this equivalent circuit, we convert the secondary side into primary side. Now as you can see in this circuit, there is no transformer. After the conversion, there will be no transformer in the equivalent circuit. So we can solve this equivalent circuit by using the Ohm law, KVL, KCL, etc. So if we want to convert the primary side into secondary side, then the secondary parameter will remain same. As we have already discussed, if we want to convert the primary side into secondary side, then we can convert the voltage source into secondary side by dividing the turn ratio, and we can convert the primary current into secondary current after just multiplication with turn ratio. Similarly, we can convert the impedance into secondary side just divided by the turn ratio. So this is the equivalent circuit referred to its secondary side, and these parameters are also in the primary side we can convert into secondary side by just dividing the turn ratio. So these are the equivalent circuit. This is the equivalent circuit in which we convert the secondary side into primary side, and this is the equivalent circuit in which we converted the primary side into secondary side. Now as you can see in these two circuits, there is no transformer. If there is no transformer, then we can solve easily these two equivalent circuits. Now there is still, to solve this equivalent circuit is little bit difficult, because this is the series branch, this is the parallel branch, and this is the also series branch. There is also, it means to calculate the overall impedance, the total impedance, it is still difficult to solve the circuit. To further reduce, to further simplify the circuit, we can solve this circuit to reduce this. This branch is basically, there are two core elements, that is RC and XM. The value of the RC and XM is basically very small, so we can transform this branch at the start of the circuit. If we transform this branch at the start of the circuit, then these four elements will be in the series, and we can solve easily the circuit. So therefore, now we will draw the approximate equivalent circuit of the transformer, in which we will transform this branch in the start of the circuit. If we will transform this branch in the start of the circuit, because the value of this branch is very small, there is the effect of this branch due to this branch is very small, nearly zero. So that's why we can transform this branch at the start of this equivalent circuit or this equivalent circuit. Now we will draw the approximate equivalent circuit to further simplify this equivalent circuit. So this is the equivalent circuit, approximate equivalent circuit of a real transformer, in which we have transformed from this branch from this point to this point. Now these two parameters are in the series, that is R equivalent in the primary will be equal to Rp plus A square into Rs, and reactance equivalent will be equal to Xp plus A square into Xx. Similarly, from the primary to secondary circuit, we have also transformed this branch in the start of the circuit. Now still it is difficult to solve this circuit to find out the overall impedance, because the effect of this branch is very minimum or nearly zero. So we can neglect this branch in the equivalent circuit, because the effect of this branch in the overall impedance is very small or nearly to zero. So therefore we can neglect this branch. If we neglect this branch, then the final approximate equivalent circuit of the real transformer will be like this. In this equivalent circuit, we just remove the RC and XM, because the effect of RC and XM are very small or nearly zero. That's why we can neglect the core elements, that is RC and XM. So this is the approximate equivalent circuit of a real transformer. This is not the exact equivalent circuit of a real transformer. This is just because in this equivalent circuit we remove the RC and XM branch elements. So this is the equivalent circuit. In this equivalent circuit, we can easily solve this circuit, because this is the simply series circuit. So we can easily solve to calculate the primary voltage, primary current, secondary voltage, secondary current by using simply Ohm law, KVL and other KCL laws. So these are the approximate equivalent circuits of a real transformer with respect to the primary side, and this is the equivalent circuit with respect to the secondary side. So that's it for this week lecture.